Once again, welcome to Adistar Lectures on Electronics and Optics. Today I will demonstrate the parameter sweep. There are obvious cases when you have to study the structure of the device by varying its dimension or varying the source angle or varying the doping concentration for electronic devices. So in those cases, parameter sweep is one of the most important thing. So here I will demonstrate the parameter sweep using a very simple example by demonstrating Brewster's angle. We know the Brewster's angle is a phenomena generally observed in case of TM polarization. The type of polarization depends on the orientation of the electric field. The source right now you are observing on your screen is oriented for TM polarization, because in this particular case you can see the propagation vector, the wave propagation vector and the electric field and the normal to the interface all are lying on a particular plane, which is the XY plane, and therefore this plane is called the incident plane, and being perpendicular on the propagation vector as well as on the electric field, the magnetic field by default perpendicular on that particular plane. At present, the magnetic field is directing towards us or towards you. This is the type of polarization called the TM or transverse magnetic polarization, because the magnetic field is transverse on the plane of incidence. Now, if you want to make it TE polarization, you just need to go to the source, right clicking on that, edit object, and change this polarization angle from 0 to 90 degree. Look at this orientation of the electric field. Previously it was lying on the XY plane, right now it is directing towards us, and by default magnetic field is lying on the XY plane right now. So this is the example of TE polarization. Here I will demonstrate you by recording the reflection which will be recorded over the length of this monitor, and I will show you in case of TM polarization there will be a particular angle that depends upon the ratio of the refractive indices between these two medium. If the wave incidence at that particular angle, there will be no reflection. The entire wave will be transmitted to the second medium. But this is not the case of TE polarization. As you can see, in case of TM polarization for various ratios of N2 and N1, where N2 is the refractive index of the second one and N1 is the refractive index of the first one. And if you are new to my channel and you are observing the first tutorial on the FDTD Lumerical, if you don't know how I have constructed these structures, so I will request you please refer to my previous videos on the basic structures and the simulation setup for Lumerical FDTD, or you can click on the card to go to my previous videos. Anyway, Brewster's angle is the angle at which the reflection will be 0, and it can only be observed in case of TM polarization, whereas in case of TE polarization, it is not the case. So before demonstrating the Brewster's angle, I need to know what will be the Brewster angle for this particular configuration. Generally, the Brewster's angle is tan inverse N2 divided by N1. Now in this case, the N2 as 2.4 and N1 as 1.4. And already you know who has followed my previous videos, this is the script prompt where I can write, I can calculate, and I can test my functions, everything over there. So here I'm going to write this N2 as this one, N1 as 1.4, the same refractive indices that I have used for my last tutorials. Here also I'm retaining those values. The Brewster's angle theta B, let's say, is nothing but tan inverse or arctan N2 divided by N1, and you know I'm going to calculate this one, so putting a question mark, and it will show you this value. But this is in radian, and you need to convert it into the degree, because the source angle we have to put in degrees, all are in degrees. So I have to convert it into the degree. Just multiply 180 divided by pi. Pi is a standard function in Lumerical, and that will give you 59.7436. So this is the Brewster's angle for this particular configuration. Now I'm going to vary the source angle starting from a value less than 59.74 to a value more than 59.7436. In order to go for parameter sweep, you have to go on your screen over there. If it is not visible by default, you have to go to view, then windows, and then these are the windows that you can enable over there or you can disable accordingly. Here there's a script file. This one is the object library. I have demonstrated in my last tutorial a little about this object library. Right now it is not required for us, and there it's come the optimization and sweep, and this is of our interest at present. Create new parameter sweep. This one is a create new optimization, so I'm choosing create new parameter sweep. You can rename it as theta variation or angle variation. Now what I'm going to sweep, I'm going to sweep both the polarization and the angle. At first case, I will check for the TE polarization by making this polarization angle, this polarization angle 90 degree, and sweeping this theta value from a value less than 59.74 to a value greater than this 59.734. I will set this polarization angle to 0 to make it TM, and then I will vary for the same set of theta. Now everything that will be done automatically. So I'm clicking on that, edit. Here you have to create new parameters what you want to vary. First case, I'm varying the angle theta. This angle theta is a variable defined by me, and it has no relation with any of the source angle or any of the parameter existing in your design or in my design. So right now I'm relating this variable, this angle theta, with the parameter. So I'm going to model, the property and object. Properties I will discuss later, that will be the sole property of the model, and the objects are those which comes under the model. So here I will choose for the objects, and you will find the source. Now these are the property, and I'm going to click on this angle theta. Right now this angle theta, the variable defined by me, gets related with the angle theta defined within the source, and I'm varying for 50 number of simulation, let's say, and I'm starting. The Brewster's angle is appearing at 59.7436, and so I'm varying, let's say, from 30 degree to 70 degree. When you want to plot the reflection with respect to the variation of the angle, so this will come along the x-axis. What you want to plot along the y-axis, that will come under this result window. So you have to add the new result. So I'm adding that, and I'm naming it R. Right now, this R is a variable defined by me, and it has no relation between any of these parameters, and I have to relate that from this result tab. So going to model, then object. My reflection is stored within this analysis group over this reflection. This reflection is the monitor which is under this analysis group. Please refer my previous tutorial regarding this analysis group and this reflection, everything. So here is the script I wrote, and where this RSIM is the variable where this analysis group is generating this RSIM, which is related with the reflectance of the reflection is recording over the length of this monitor. This RSIM becomes the property of the analysis group, and from here I have to call that property, or I have to relate this property. So here I'm naming it R. This is a new variable, and I'm going to relate. This is the analysis group under the model. Under analysis group, you have two things, result and object. But I'm going to click the result. Automatically, RSIM is available over there. So I'm clicking on that. So at every simulation, the simulator will record corresponding value of the reflection for a particular value of the angle. And after that, the plot will appear automatically. The source angle I set to 90 degree. So by default, it will be TE polarization. Now I am interested to record all the data for TE and TM both simultaneously, and that will be automatically by sweeping the parameter. So therefore, I need to initiate another parameter sweep, and that parameter sweep will be for TE and TM. So I have to right click on that angle variation and insert parameter sweep. So this parameter sweep is coming above this angle variation. Now rename it as polarization sweep. You may think this type of things as a nested for loop or nested parameter sweep. If you have any idea of any programming language, so you have an idea of nested for loop or nested loop. So this is a similar thing. So here I'm going to click on edit. So this value I'm going to change from range to value, and the value I'm going to set for 2, and this is a parameter pole, any parameter you can define. Now model, object, source, and here I am choosing the polarization angle. First value is 0 and second value is 90. So for first value, it will be for TM polarization. It will record the data for TM polarization, and when it will switch to the value of 90 degree, the simulation will be done for the TE polarization. I want to observe the same thing. Here I'm relating this R, but right now this R will be called from its child sweep. So its child sweep already have a variable R, and that is related with this reflection. And when you are initializing the parameter sweep as one of the parent parameter sweep, the parent parameter sweep will automatically show you the available result under its child parameter sweep. I have right now only one for its child parameter sweep, which is R. And finally, I'm clicking OK. So once I will click run, you will see that when the theta will be 0, the angle will vary from 30 to 70 degree and there will be 50 number of simulation. Then the polarization angle will switch to the 90 degree and the same simulation will be done over here. So therefore, the number of simulation in this case will be 50 times 2. You are going to initiate 100 number of simulations. Before running this one, I need to mention another important thing, the boundary condition. Previously, when I have simulated this structure for TM polarization, normal incidence TM polarization, I set the boundary condition as periodic. Periodic boundary condition is applicable only when the injection axis will be parallel to the Y boundaries. But right now, the injection is going to make an angle with respect to the X axis. So therefore, the periodic boundary condition will not be applicable. You have to set the block boundary conditions and now run it. So as you can see, this is the first run. By making this polarization, TM polarization, the angle is varying, and right now theta goes to 90 degrees, making the polarization TE polarization, theta is varying for the same set of angles. Now the simulation is completed, and to observe what is the result came, just right click on the parent sweep. In this case it is the polarization sweep, and go to the visualize. So in this case by default is a two-dimensional plot is coming. In order to see the curve, 1D curve, you have to click on the line. This one is the angle theta variation, so just changing to x-axis, and this one is a slice. This one is for the parent sweep, that means the polarization sweep. So first value is 0, which means it is the reflectance for the TM polarization with respect to the angle theta. So as you can see, the 0 value of the reflection is coming for theta is equals to around this. So our theoretical value came as 59.74, close to 60 degree, and as you can see this value is coming close to the 60 degrees, 59.5, 59.7. so around this value it is coming as 0. So it is matching with the theoretical result, and this is for TM polarization, and for TE polarization just changes this value from 0 to 90, and this is the TE polarization. For TE polarization there is no such angle for which the reflection can go to 0. Let's visualize the propagation of the wave through this media while incidenting at the Brewster's angle with TM polarization and at the same angle with TE polarization. And thereafter I will show you what happens when the TM polarization incidents at the Brewster's angle and at the non-Brewster's angle. So for that I'm going to the monitor, and there's a movie monitor. I'm just scaling this movie monitor to fit within my screen, and a few changes I need to do in order to get a better visualization. I'm going to the source, and this frequency or the wavelength I'm changing from 0.5 micrometer to 0.1 micrometer for better visualization. And in case of TM polarization or TE polarization at Brewster's angle, wavelength is not going to matter. And thereafter I'm changing the boundary condition for FDTD. Now look, while I was scanning the angle at TM polarization or TE polarization, then I need to keep it block boundary condition. But right now I want to see how the wave incidents at the interface and how the reflection takes place, how the transmission is taking place. So in order to observe that thing, I'm just changing from block to PAML. Well, you can keep it block boundary condition, but keeping block boundary condition, you may not visualize the incident wave incidenting at a particular angle. You can test it by yourself. So that's why I'm keeping it the PML boundary condition over there to visualize my wave in a better way. And with that I'm changing my source much closer to the interface. So my polarization is TM, incident wave is at this is my Brewster's angle. So the wave gets incident at the Brewster's angle, and I'm running. As you can see, the wave is incidenting at this interface with an angle, and nothing gets reflecting back, everything gets transmitted. So no reflection. Well, now let's see what will happen if I change the polarization. So I'm changing this polarization from TM to TE. You will see a clear reflection while the wave is incidenting at the same angle, but is the Brewster's angle. Now this wave gets incident, and this is the reflected wave. As you can see, this is the reflected wave. So I hope you have understood how the wave gets reflected if it is not the TM polarization. Now let's do another experiment, that I am keeping the source TM by making it 0, and I am changing this theta angle to say 30 degree. That means not the Brewster's angle. and I'm running this one once again. While the polarization is Tm and the incident angle is not the Brewster's angle, it is at other than the Brewster's angle. So as you can see, this is the reflection. The wave gets reflected since the wave is Tm, but it is not at the Brewster's angle. This was the first example of the parameter sweep. So in order to get much more exciting tutorial on the Lumerical FDTD, stick on my channel. Thank you very much.